Welcome everybody once again to this third section that we have today at this event, where we would look into case studies or pilot projects, research projects on the use of green hydrogen in mobility and transportation systems. And I have here three speakers with us. We have Mr. Sammy Wittop from the National Organization of Hydrogen and Fuel Cell Technology, the now GmbH, and we have Mr. Dr. Daniel Markthaler, who is working at the Fraunhofer Institute of Manufacturing Engineering and Automation, which is also known as Fraunhofer IPA, and we have Professor Dasappa from the Indian Institute of Sciences. We will have the order of Mr. Wittop starting with his presentation, then I would request Professor Dasappa and then Dr. Markthaler. And before I hand it over to you, I would like to shortly introduce all of you. So Mr. Wittop, Mr. Sammy Wittop is a researcher with experience in the energy industry and has been consulting energy companies and municipal utilities for several years now. Since 2021, he works as a program manager for international energy concepts and international cooperation department of the now GmbH. He's responsible for project initiation, implementation of export initiative of environmental protection, which is the funding program of the German Federal Ministry of Environmental Protection. Thank you, Mr. Wittop, for taking out time for this event. We're looking forward to your presentation. Now, Professor Dasappa, who has been a faculty at the Center for Sustainable Technologies at the Indian Institute of Sciences in India, and his area of research is solid, liquid, and gaseous fuel combustion and combustion science and technologies. He has many publications and national journals and books to his credit, or more than 18 patents as well, and has been involved in the technology transfer initiatives of bioenergy devices in India and abroad for many years. Professor Dasappa, very warm welcome to this session, and thank you also for taking out your time today to being at this event. Then I move on to Dr. Daniel Markthaler, who is a research associate for hydrogen technologies at the Fraunhofer IPA in Germany. His current work focuses on active development of hydrogen technologies, especially in the simulation of fuel-based cell systems and digital twin development on systems level. Very warm welcome to you as well, and thank you. We're looking forward to your presentation. Fraunhofer is also a very strong network partner for us, so if the colleagues are here from Fraunhofer in India, thanks a lot for your support as well. I would then hand it over to Mr. Wittop for his presentation, and for the audience, after these three presentations, we will have some time for Q&A, so please drop in your questions in the chat box or Q&A box, and I will be able to take that over afterwards. Now, I request Mr. Wittop to share his presentation.
Thank you very much. Pleasure to be here on this symposium. And let me just share my screen. Yeah, perfect. I hope you can see the screen.
Yes, perfect.
Thank you. Yeah, my name is Sammy Wittop, Program Manager, International Energy Concept at National Organization for Fuel Cell and Hydrogen Technology. And then I want to tell you today something about the hydrogen, the mobility sector and hydrogen, and also want to give you some insight of the current state in Germany. But first of all, I will start by framing this presentation by giving you some insights of the National Hydrogen Strategy, which was started in 2022 by the German federal government, which decided 38 measures along the whole hydrogen value chain. On the left side, you see all these measures, starting with hydrogen production, hydrogen applications in the mobility sector, industry, heating, hydrogen infrastructure, the research and development of hydrogen systems, and also outside of Germany, the European hydrogen activities and the international hydrogen markets. This hydrogen strategy started in 2020. The first phase up to 2023 was focusing on the start of the market ramp up in Germany, harness opportunities, make pilot projects in Germany, and from 2023 onwards to 2030, the second phase is focusing on the strengthening of the market ramp up and also ramp up of national, international hydrogen activities. But today we don't look at every measure. We look into the 9 measures of the mobility sector. And here you have an overview of all these 9 measures in these boxes. And the color codes on top of the boxes are linked to the pictures on the right side. Black would be fuels, hydrogen fuels. So measures related to hydrogen fuels and static fuels. Red is infrastructure. So for example, the hydrogen fueling stations. And in yellow, you see the vehicles or applications related to hydrogen mobility. The federal government use these measures to orientate, to implement their hydrogen funding programs to ramp up the hydrogen technology in Germany. And to give you an overview of some hydrogen funding programs, we have a look into the funding programs of the Federal Ministry of Transport, BMDV. And the BMDV focuses on funding programs along the whole hydrogen value chain, starting with hydrogen production and electricity-based fuels. The funding volume here is up to 1.5 billion euros until 2024. Commercial vehicle funding guidelines have a funding volume of 1.3 billion, also up to 2024. Buses gets funded up to 1.2 billion, also until 2024, and railway stations gets funding of 224 million euros. In the lower part of this slide, you see the different funding programs of the Federal Ministry of Transport, starting with Highland Hydrogen Regions in Germany. This is a very interesting integrated funding program of the Federal Ministry of Transport, which focuses on municipalities, regions in Germany, which try to enable the whole hydrogen economy in their area. We will look into this funding program on the next slides a bit deeper. IPSAI would be important projects of common European interest. It would basically mean we have large hydrogen projects, role model projects in Europe, which gets a big funding to showcase that the technology is ready and to see in which cases this technology makes sense in Europe. On the right side, the National Innovation Program, NIP, which was started in 2016 and is already in the third period. This funding program is differentiated in 2 pillars. The first pillar is the funding guideline for research and development, and the second one is for market activity and market ramp up. The idea here is that through these research and development pillar, you activate or you fund the production of hydrogen technology, hydrogen applications, scale up the production. And on the other hand, the second pillar is focusing on ramp up the market to create demand for these new technologies. With this said, I want to jump into the Highland regions, the Highland funding program. Highland, as I said, is a funding program also by the Federal Ministry of Transport, which is focusing on municipalities, regions in Germany, which want to implement their whole hydrogen economy throughout the whole hydrogen value chain, starting from electricity production, out of green energy, the production of green hydrogen, the transport and storage of this hydrogen, and the distribution of the hydrogen through fueling stations, and also the different applications which can be tested through this funding program in the different regions, for example, hydrogen buses, heavy duty. This Highland program, as I said, is focusing on municipalities to enable their own hydrogen economy. This program is two steps, more or less, 3 steps. The first would be high starter. If a municipality don't have any experience with hydrogen, but they see a huge potential in their region for hydrogen applications, they would apply for this Highland program and would start as a high starter to get experience from other Highland regions and to think about ways how to implement hydrogen in their municipality, in their city. The second step would be high expert. High experts have a bit more experience in the hydrogen area, and they maybe have already some pilot projects ongoing in their regions. And through this Highland program, they get now a funding up to 400,000 euro to create their own hydrogen concepts for the hydrogen economy in their region. And the last step would be high performer. High performers are mature in the hydrogen sector, have already some hydrogen technologies implemented, and they're now implementing the whole hydrogen concept, implemented hydrogen concept in their community. And this Highland program is very successful. It started in 2019 to 2021, the first call for the Highland program. We had 25 regions in Germany and have supported with around 67 million euros. And to show you the 3 high performer regions, the first one was in Oldenburg, the northern part of Germany, where Oldenburg focuses on future ways for mobility, hydrogen mobility. The second high performer was in the Rhein-Neckar area, where the municipality focuses on applications, hydrogen applications in this area. And the third high performer was in Bavaria, near Munich, where a municipality become a model region for integrated hydrogen projects. And the second call for Highland just started this year. We had 65 applications for the high starter level. And out of these 65, we choose 15 municipalities, which now starts to think about how to implement hydrogen in their economy, into their region. And on the right side, we see the high experts. We had 55 applications for the high expert level. Out of these 65, we also choose 15 municipalities, 15 cities in Germany, which become high expert and now gets funding up to 400,000 euro to create their concept, the hydrogen concept. And to wrap up with this Highland funding program, I want to show you the benefits of it. On the one hand, we have the thing that hydrogen regions start to talk about hydrogen. They work with hydrogen and think about how to implement hydrogen in their regions. We also have the connection aspect between the regions. So more mature hydrogen regions are somehow role models and share their experience with regions which are maybe not so mature in hydrogen yet. And we also have this huge networking character between all these regions, the visibility the regions get through this hydrogen network. And to wrap up my presentation, I want to give you some numbers about the deployment rate and the infrastructure in Germany, the hydrogen infrastructure in Germany. These numbers are all based on funded applications. So starting in the first row with the fuel cell vehicles, current state, November 2022, we have over 2,000 vehicles implemented in Germany, mostly via the funding program NIP, National Innovation Program. Fuel cell buses, we have around 70 buses implemented. Fuel cell trucks are 29 on the road right now. Forklifts, so intralogistic is a very quickly growing market where you have 180 forklifts implemented plus 150 are in implementation right now. And the final topic I want to show you is the refueling stations in Germany, the refueling network, hydrogen refueling network in Germany. This is one of the most mature fueling networks worldwide. We have different pressure levels in Germany, 700 bar for passenger vehicles and 350 bar for heavy duty. And to make this more visible for you, I want to show you these two graphics of Germany. On the left side, you see the 700 bar network for passenger vehicles. Passenger vehicles need a more compressed hydrogen because they have smaller tanks. And the 350 bar for buses, they have larger tanks, so they don't need such a high pressure level. And interesting here on the left picture, you see in the western part of Germany are the most dense infrastructure of charging networks, refueling networks, because there's a lot of industry in this area, so we need a lot of refueling stations here. So I hope I could give you some insights about the current situation in transport in Germany. If you have any questions, feel free to contact me. Thank you.
Thank you. Thank you, Mr. Wittop. That was a really nice overview of the work that you do in mobility and green hydrogen. We will keep the questions at the end. I would like to now ask Professor Dasappa to give his next presentation.
I will just talk about a subject which probably is not really attended to in many hydrogen forum. I am just trying to look at can biomass be a source, because while this is made a passing remark in many fora on green hydrogen, but I think not much attention is being paid. I thought I should just look at this as a resource and trying to see how we will be able to meet the demands at least partially as a distributed mode for many of the applications what we have been looking at. Coming to the institution, I represent an institute which is 100 plus years, established in 1909. It's one of the premier institutions in India and ranked pretty high across the globe in terms of its capability. It just generally looks at both science and engineering. And very recently we started off undergraduate. Otherwise, we do mostly the post-graduation and mostly the doctoral degree is what we have, about 4,000 students and about 500 faculty members. In this broad description about the institute where I come from, but when we really look at any of these hydrogen or hydrogen related aspects, I think one very clearly, I think it also came up during the early part of this meeting, wherein you look at the so-called steam methane reforming as a benchmark. If you look at the chemistry, you theoretically can get close to about 500 grams of hydrogen per kg of methane, but in an actual system, depending upon the capacity, you can get anywhere between maybe 250 to 300 grams, or equivalent of about 3 to 4 kilograms of natural gas is required to generate a kg of hydrogen, during which the possibility of emitting close to about 10 kgs of CO2 is expected. And the same thing, apart from being hydrogen, I think it also becomes a derivative for various downstream chemicals, which we keep seeing in the industrial applications. And to some extent, I also should say that there are challenges even for an SMR process, which has generated hydrogen rich syngas and separation, and meeting the requirements of a fuel cell is of tall order. This is something which we need to keep in mind. Most of the fuel cells which have been operated have been done using other resources which you get clearly from the electrolysis or something similar, But very limited work has been done to see whether, it's not that it's impossible, but very limited work has been done with an SMR process which going into a fuel cell. Keeping this in mind, I thought I should just introduce another fuel which is called biomass, which is a carbon hydrogen matrix, which is one of the other naturally available resources wherein you have hydrogen as an element, like water is other natural resources. When we really want to look at compare biomass with the methane, biomass contains about 65 grams of hydrogen per kilogram, while methane has about 250 grams. And maybe water, I think previously mentioned, it has about 100 grams of hydrogen per kg of water. This is what you can really look at. Majority of the fuels will have similar, I should say, carbon, hydrogen, oxygen on an ash-free basis. That means, theoretically speaking, you should be able to get on normalized basis a similar gas or similar hydrogen yields from most of the fuels on an ash-free basis. This is something which we need to keep in mind. But majority of the, I think, community across the globe started looking at biomass to power, which probably is the lowest yielding efficiency component. And in the recent times, and even in India, we started looking at, because we are also at starved of electricity in some pockets of the country, and in some pockets we are all super rich in electricity. I think these are some things which, because India being whatever size it is, it seems to be having its own issues which needs to be really looked at. And that's how I think majority of our work also looked at distributed power generation using biomass. And there are challenges in India with respect, if you really look at large scale, unlike the West. And as you know, majority of the biogas or related aspect is looking into. This is a nice plot wherein you have biomass, and if you have end use like boiler or biomass integrated gasification combined cycle, that is gas turbine route, you can get a better efficiency. People have been looking at, can we really go to hydrogen, which can be conversion efficiencies close to 60%. If you club with the fuel cell power, can it be closer to 45%? I think these are some things which become very, very important. And probably maybe another component which can come into this is the chemicals like methanol or ammonia, and maybe the SAF, which is being very, very important. When you really look at biomass, there are two ways to get to gaseous form. One, the biological route, which typically yields methane, but you could really control the process to see whether you can get hydrogen too, but that is in a very, very extremely slow rate. Thermochemical conversion process through gasification, it's a substoichiometric process. You will be able to get a mixture of gases, and those mixtures are related to the kind of chemistry what you see here. You have biomass, theoretical limit is about 150 grams per kg of biomass. If you try to do a magical reactor wherein you put certain moles of oxygen, certain moles of steam into that one, you should be able to extract all the hydrogen which is there in biomass and the water as hydrogen in the form of gas. You can realize that. But in most of the technologies, probably across the globe, and we ourselves have been looking into power generation through air gasification, you can extract about 40 to 45 grams. That means from 65 grams, you can get about 40 to 45 grams. But I think the theoretical limit, if you can do a good chemistry there, you can go to 150. But at IISc, we have been able to achieve in excess of about 100 grams of hydrogen per kg of biomass, based on the earlier work what we had done on air gasification and moving into space with respect to oxysteam, so that you can eliminate nitrogen. These are glimpses of power projects just to give you an idea of scale up has been done at megawatt level with respect to the power generation. And this work what we have been doing is not way widely off from that in terms of scaling and other things. That means even if you want a scaled up version with respect to hydrogen, there should be a possibility. And the gas quality what you see is capable of operating on turbocharged engines, which probably is still not as acceptable for a fuel cell, which you will see in the subsequent slides. What we could do is, from biomass, you have CH1 is to 1.4 as a carbon to hydrogen ratio, unlike what you get for steam methane at molar basis, air gasification, you get to CO to H2 and oxy steam. You can go, this is something which probably is very, very useful when you want to do the synthesis of this gas into chemicals or some sort of thing. The CO to H2O ratio can be controlled so that you can get into methanol or any other downstream products. When we go into so-called hydrogen, probably I think you can really look at all the carbon needs to be eliminated so that you will be left with only hydrogen. And today we have achieved a process wherein with process control parameters, you should be able to achieve different gas composition by controlling the process within the system. And we have tried out with a medium density like wood chips, a very high density called coconut shell, and a very low density called corn cobs. I think these are the feedstocks which have been used, and you have been able to get gas compositions which is all these data is intermingled with all the three processes which are there. And this is what we want to see whether we can replicate what an SMR process is doing with a fossil fuel, which can be replicated using a biomass which has a very low C and H2 ratio kind of situation. I think it's something which we have been looking at. That means we can look at all the necessary chemicals which can be really generated using such similar things. Our major target was to see whether we will be able to get the so-called specifications for fuel cells. I think that has been a challenge. Probably it's not only in India, across the globe actually. Today we have been able to meet the ISO specifications to operate a fuel cell using hydrogen generated through a thermochemical conversion process, and we have established the entire protocols for evaluating this quality. And here you see a plot wherein the ultra pure hydrogen, which is shown on green, and the biohydrogen on the blue and on the yellow one, we have done enough number of hours to show that yes, there is no degradation of the fuel cell irrespective of what fuel you take, either the ultra pure hydrogen or biohydrogen. We believe that today the technology is available, and as far as IISc is concerned, within Indian context, I think we are wanting to set up a 10 kg per hour hydrogen generation capabilities to fuel a fuel cell bus, which is going to shuttle between maybe some parts of Delhi, very important places in Delhi. This is something which is coming up. While I'm talking about the technology, there is also a sort of a concern showcased by various groups across the globe saying that is biomass based generation of hydrogen green or what needs to be. And if you really look at the global warming potential of any of these things, if you have a rotational crop of 1 year, the GWP is 0. And even at the end of 10 years, the factor is 0.04. I think this is something which we need to be aware of. And with the kind of technology what has been developed today, probably we can be carbon negative because CO2, which is coming out as a mixture of syngas, can be separated out for utilization. And we can also sequester a certain carbon amount, activated carbon, which comes out as a byproduct, which can turn out to be a carbon negative as a process. This is something which I thought I should share with the larger audience. I think I'll stay put here and looking forward for any questions or observations on this. But I should say that very few groups across the globe have been talking about biomass. I think India being whatever is agro-based economy, I think, and there are many other countries across the globe which will be able to do this one. Thank you very much.
Thanks a lot, Professor. Thanks a lot, Professor Dasappa, for this, for introducing us to this niche project that you are working on. We will keep the questions to right at the end. We have one more presentation to go, and for the audience, if you have questions, please type them into the chat window. Please also say who the question is for amongst these three experts, and I can take that up right after this. Now, I would like to welcome Dr. Daniel Markthaler for his presentation. Please start with it. Thank you.
Yeah. Thank you very much also for the possibility to give this talk today. I will talk about the EcoFCGen project as a use case. It is basically about the development of a decentralized power generator using fuel cell technology. And before I'm going to start, I would kindly ask you to keep the information from this presentation confidential, meaning if you would like to reproduce it, please contact us first. And let's have a look quickly on the agenda. We'll start by a short introduction, just that you know who we are. Then the main part of the talk will be about the project itself, of course, where we'll highlight some of the research questions and also technical aspects. And in the end, I will give an outlook to see or to show you where this genset, which is built in this project, could be used for in the future. So I'm working at the Fraunhofer Institute for Manufacturing, Engineering and Automation, short IPA, in Stuttgart. And the IPA is a very big and diverse research institute.
2019 SAP ಬಂದಾಗ ಹಳೆದಿಂದ they have to commit
I'm sorry for the disturbance. 1 minute.
No problem.
Professor Dasappa, could you unmute? Yeah, thank you. I think there was a disturbance from the earlier speaker. Please continue.
Okay, so yeah, the IPA is very diverse research institute. So we have 6 major working areas, which is network production, manufacturing and process engineering, intelligent automation, medical engineering and biotechnology, surface engineering, and then also resource efficient production. And this is the area where most of the hydrogen projects at IPA are associated. I'm working in the Hydrogen Technologies group. We are a newly founded group. Currently, we are 5 people, including myself, and we have currently 3 major research areas, which you can see here. So on the one hand, multi-scale modeling and simulation. So really going from a very small scale, detailed electrochemical simulations to large scale on a systems level. It also involves a lot of digitalization projects, such as development of digital twins. On the other hand, we are concerned with hydrogen technologies in production, such as manufacturing of fuel cells and electrolyzers, and also recycling is a big topic. So where we ask ourselves, okay, what happens with the key components at the end of their life? And at the IPA, there are several hydrogen projects where a lot of groups contribute to, but in principle, you can cluster it in 4 main sectors, I would say. One is biological hydrogen production. Biological hydrogen production based on biomass. On the other hand, production planning and automation, such as the factory planning for fuel cells and electrolyzers here. Especially robotics are of importance. Also, a lot of projects involve digitalization and artificial intelligence. And the 4th sector is the industrial application sector, where we develop energy supply concepts for with hydrogen as an energy carrier and storage. And this EcoFCGen project belongs to this category. Now let's have a look at the project itself. So it's funded by the German Ministry for Environment, Nature Conservation, Nuclear Safety and Consumer Protection for a period of 3 years. It started in January this year. The project is supported by the National Organization of Hydrogen and Fuel Cell Technologies, the NOW, as well as the Zukunft Umweltgesellschaft, ZUG. And here under this link, you can get more information about this project. Here on the right-hand side, you see the partners which are involved. It's the CPC company, which has the lead for this project. We as the Fraunhofer IPA, as well as the University of Bayreuth. So I'll start by giving a quick motivation for the project. All of you know, combustion engines, they are involved in several energy sectors, such as automotive or energy production. And you also know, to reach our climate targets and to prevent further global warming, this situation have to change. So there are a lot of efforts to replace the combustion engines, such as diesel engines, with battery and fuel cell technologies currently. So we are on a kind of transition, which will still last a couple of years. But the final target, of course, should be that we end up with a green energy production scenario. And in this project, we focus on the fuel cell component, or on the fuel cell technology. So what are the goals of this project? It's summarized here. We will develop a fuel cell-based generator set, or short genset prototype, for decentral energy supply, so that you can use it, for example, as an emergency power generator, or in areas where you have no connection to electric grid. One of the research aspects is to evaluate different climate and environment conditions on the system itself and on the component level. Therefore, 2 prototypes will be built, one which will be tested in Germany and the other in India. And from data which we collect from the testing and afterwards from disassembling the devices, we hope then to evaluate the impact of the different environmental conditions. A big part of the project, and this is something where most of the work of the IPA will be done, is the development of a digital twin, or a first version of the digital twin. I called it here digital shadow of the device, with the idea that you can use such a digital twin at some point for predictive maintenance, for example. And also another important point will be the development of circular economy strategies for the key components. And it's also important to say this. So in this project, we will end up with a real product. You can see this, the sketch here, a real product, a genset, which will also be introduced into the market. Now let's highlight or talk about some technical aspects. So we bought the fuel cell from Toyota. It's the same which they use for the Toyota Mirai. And here you can see the different components, the fuel cell stack, the pumps, air compression, and all the control units. And all of them, they are put together. They are assembled in such a nice black box here. And from an research perspective, it will be interesting to see how these fuel cells, which are actually designed for the automotive market, will perform under stationary conditions. And it's also important to keep in mind the fuel cell, of course, is the heart of the developed genset, but of course it's not a whole story. There's a balance of plant. You need You need power electronics, you need an inverter, you need a buffer battery to smoothen out peaks in power request. And all of these considerations are part of the design and engineering phase. And here you can see a first draft of the genset, how it will look like. So it will be a containerized solution, meaning all the components, they will be put in a weatherproof container. And the idea is really that you have a plug-and-play solution. Yeah? So if you have a hydrogen supply, you just put it in with a proper connection and you get electricity out. Here, on the right-hand side, you see some technical specifications. So this genset will deliver between 50 and 60 kilowatt continuous power. For shorter times, can also deliver up to 100 kilowatt, which is due to the battery. It requires this 3.6 kilogram per hour of hydrogen at 60 kilowatts with high purity. And yeah, so the idea is for this project, will be controlled and monitored completely remotely. So there should be no babysitting necessary. Principle. As I outlined already, one of the major research aspects will be the development of a suitable digital twin. Here you can see a schematic diagram of the major components with the fuel cell in the middle, the power electronics here, cooling system here, and if we put in the system boundaries, you see this is the genset in principle. And now if you start if you want to model this, of course, the first thing you have to do is you need models for all the major components, validate them, and then bring them together. And once this is done, you also have to think about interfaces such that it can communicate with the sensor data obtained from the real device. So this shows you the concept of the whole digital twin. Here some timeline. So currently we are in the engineering phase of this genset, which should be finished somewhere in the beginning of next year, so in the next months. What we defined so far are we selected proper sensors for the digital twin and thought about which parameters are necessary. And so we are currently in we're doing the model development currently. And once this is done and we have the first prototype done, then we can think of the interfaces, the communication, and of course the real field test, which will be done somewhere at the end of next year. The real field test will then be the basis for model refinement also. And all the data which are collected during this field tests from the two prototypes in Germany and in India, they will be analyzed in the last stage of the project. And as I said, we will try to correlate this also with the different environment conditions and lifetime and performance differences. And the second aspect, and this is mainly done by the University of Bayreuth, will be the development of suitable circular economy strategies. So for this, it's important to keep in mind that currently the stack lifetime is really one of the limiting factors for the commercialization of fuel cells. And what will be done in the scope of this project is to develop a decision tool based on sensor data, which allows you to detect if a certain component has a problem, and then also to suggest and identify proper circular economies. So, so if we see a certain component has a problem, we have to replace it. But what happens then? Can we repair it? Can we refabricate it? Does it have to be recycled? such things involve economic and ecologic considerations, of course. And the idea is that the whole operation time is optimized and becomes more sustainable also. And now I would like to give a outlook. Okay, what can we do with this genset once it is done? So as you see, the heart, the major component is the fuel cell. We have then our genset. It can be deliver heat and power. Heat is also can be of value. Could also be used as a fast charging station for electric vehicles, for example. But the question is also, how can you implement such a device now into a whole green energy concept? And one idea could be the following. If you think what are the next steps, if you think also about hydrogen production, not only the usage but hydrogen production, let's assume we have photovoltaics to produce electricity. This goes into an electrolyzer, and which produces hydrogen with a kind of central storage, hydrogen storage, and then we have our genset, which delivers heat and electricity, or in this case, a kind of charging station. This could be used, of course, for infrastructure such as farms and mines and construction sites, wherever you need electricity and heat. Also, in the electrolyzer stage, okay, you have a lot of excess heat, which can be or which could be used. The electricity from the photovoltaics could also be used directly, for example. Then, in between, there can be a battery storage, and you also might have fallback options from the electrical grid. And of course, there's also water produced in the fuel cell, which can be used, for example, for the electrolyzer. And to connect all these things, what you really need, if you want to design such a kind of microgrid, is a smart central control system. And I think such solutions have a great potential to provide a valuable contribution in the energy market. And there's a lot of developing potential currently. With that, I would like to end. Thank you for your attention, and I'm open for questions.
Thanks a lot, Dr. Markthaler. This was a very, very comprehensive presentation of your projects, and it's wonderful to see that you already have cooperations with India in these areas. I would like to ask the audience to type in their questions if there are any, and I would also, one moment, I see, yeah. And also Mr. Wittop and Professor Dasappa, if you could also be here for any of the questions that we have to take. Right, that would be great. I have a question for Mr. Wittop already. So thanks a lot for the presentations. One question we had was, are these projects that you have at the Now GmbH just focusing on Germany, and do you see that there's a scope for any international connects there?
Yeah, thank you. Very good question. So as I showed you before, the hydrogen strategy is focusing on Germany, but also on international markets, European international markets. And for example, the project which Dr. Markthaler presented, EcoSDGen, is also a project which is a funding project by the Federal Ministry of the Environment, which is focusing on export markets and international markets. So they're definitely the aim to address other markets outside of Germany with technology from Germany.
All right. Thank you. Thank you for that answer. There was one more question that came in, I assume, during your presentation. So it was, so apart from CNG to hydrogen routes, transport and utility, what would be a sustainable route for scaling up hydrogen production and utilization? And this also is perhaps also in the Indian context to Professor Dasappa. This could be a question.
Yeah, see, actually, I have been fighting for level playing field of in the space of hydrogen, along with you look at every program or every conference is focused more on electrolysis. I think we just would like to see whether biomass also could play a role, and definitely it will have its own sizable contribution as we move forward. On that, there is no second thoughts, but I think we just wanted to make sure that this also gets the space for its application, and it could be distributed. We don't have to really look at we are going to replace all the hydrogen which is going to be done through fossil or whatever it is. But I think we are just looking forward for the space. Yes, there are umpteen opportunity to scale up. I think that question will come as we move forward. Only thing is the work at IISc has shown that yes, we can really target something close to what PEM fuel cell requirements are. And we can also look at derivatives coming from whatever the steam methane reforming is doing for downstream chemicals like ammonia or methanol or various other things is definitely a possibility. That's all we are at the stage, but I think scale up is definitely possible as long as there is enough policy enabling mechanisms which can really drive this one. We are looking forward only for that one.
Okay, thank you. Thank you, Professor Dasappa. I'm checking the audience chat and Q&A. Audience, if you have any questions, please type them in. We have a couple of minutes here to take up questions from you.
There is a question related to biomass. I just thought I should just answer that one.
Yes.
It's carbon hydrogen matrix. Currently, we have been looking at agro residues as the thing. It needs a bit of conditioning which has to be done. While for vegetable waste, there are alternate technologies people have been looking at, especially in the Indian context or European one, because they are converting into CNG equivalent, which also has an offload onto a pipeline. Here in India, I think IOCL is buying them. The wet mass can get into maybe bio-CNG, which is apt, and maybe something to do with dry and municipal solid waste combinations can get into the thermochemical conversion, which can also be converted to hydrogen kind of situation. I think this is something which I thought I should just let the audience know that.
Thank you. But someone's asking a very preliminary question as to why has biomass not been considered so far? What are the major barriers to look at it for H2 production, like seriously as one of the resources?
Unfortunately, maybe there are multiple things. There are not many players who are trying to push biomass, especially in the Indian context. That is one thing. But I think second one is there should be some visibility for this to happen. That may not have happened, maybe both in India and elsewhere. That could be one of the major reasons. That means you need some strong lobbying to be done to bring into attention many of these things, whatever has happened. We are looking forward for such a thing, and biomass can play a critical role both in terms of eliminating the otherwise CO2 generated by degradation, or plus it can also replace certain fossil fuel in terms of decarbonizing various industrial sectors. I think it can play a very critical role unless until policy enabling mechanisms do play its own, I should say, initiatives to make sure biomass has a level playing field.
All right, thank you for the clarification. Mr. Wittop, were you saying something?
Yeah, I would just agree to Professor Dasappa's Professor Dasappa, because you should always, if it comes to hydrogen production, you shouldn't look on just maybe electrolysis as the only way to produce. There are definitely different ways to produce the hydrogen, and you should look at every possible way. In Germany, for example, water cleaning instructions also start to look at producing hydrogen out of biomass. So there are definitely different ways which should be taken into consideration when it comes to hydrogen production.
Thank you. I see that there are no further questions for these presentations, which means then we have come to an end of this event. And there have been feedback coming in from a lot of participants. I'm also writing privately, saying that the presentations were very insightful for all of you. Oh, I see there is just a question popping up, sorry. So it's a question looking at, so this must be for Professor Dasappa, likely, that the disposal options for waste from thermochemical conversions when you look at so biomass green hydrogen. Professor Dasappa, I'm not sure you heard me.
Sorry, okay. Sorry, I was muted. I see that question. What are the disposable options for waste slurry from thermochemical conversion? I think I just would like to mention here the process what we have adopted has very little with respect to any of the tars which are going to be generated. That is one of the major hazards which is going to be there. Otherwise, it's going to be some dust which has to be handled along with ash. It is easily handleable so that we will be able to meet all the necessary emission standards in a given environment.
Right, thank you. There's a very generic question here now, which may have been addressed before, but can one of you, perhaps Mr. Wittop, address Germany's plans on onboarding hydrogen generation for rail transport? If there is any new information, yes.
Hydrogen generation for rail transport was the question.
Yes.
There are different pilot projects ongoing right now for rail transport. I'm not sure which city it was, but there definitely Siemens, for example, is working on this very heavily to create rail transports based on fuel cell or hydrogen.
Right, thank you. All right, then I think we have come to an end of this session and then come to an end of this event. Then I would like to thank the three of you for taking out time, and thanks a lot for giving us the overview into your projects at your institutions. This was very insightful for us to see what ongoing research and larger projects also in terms of policy are ongoing in India and Germany. For the audience, we will make the sessions available here. The sessions have been recorded and will be made available. If any one of you has, Mr. Markthaler, you had said that there might be information that you may not want to be reproduced. If you have any concerns regarding the recording, please let us know. Otherwise, the event will be made available to the public in the next days on our on our website, I'm sorry. And if there are any questions, perhaps one of the audience members contacts you further over email. So with that, thanks a lot. And then I also thank all the DWIH supporter institutions that have helped us build up this event with their resources and suggestions for speakers and content. So thanks a lot to them. And then I wish all of you a nice evening and a nice day ahead. Thanks a lot. Bye.
Thank you. Bye.
Thank you.
Yeah.
Bye.